Beneath the surface of the water lies the heart of an operating nuclear reactor. The blue glow is made by gamma rays emitted from the source of radiation and is known as the Cherenkov effect. This glow identifies the active core of a pool-type reactor. One of four basic types of research reactors, versatile tools of nuclear exploration. Another is the tank-type research reactor, with the core buried deep inside a thick concrete shielding. A third type, the Aqueous Homogeneous reactor, has a small steel vessel containing liquid fuel deep inside a reflector of graphite blocks and a shield of concrete. The fourth is the graphite moderated type, a research reactor in which the core itself is a huge cube of graphite and fuel surrounded by concrete. Research reactors of all types have in common the means of providing access to the core for irradiating samples and conducting various experiments. Beam holes extending into areas of different neutron flux intensity, vertical irradiation tubes, through tubes extending directly through the core itself, rabbit tubes operated pneumatically or hydraulically, allowing rapid insertion and withdrawal of samples, irradiation tunnels for the exposure of large objects, including animals, to lower neutron fluxes beneath the core, and thermal columns of graphite, where large volumes of thermal neutrons are easily accessible. Throughout the world, research reactors of the types described, and modifications of these types, are being used at various locations. The operation of the first pool-type reactor began at Oak Ridge National Laboratory in 1950. Since then, this type has gained popularity because of its simplicity, flexibility, and moderate cost. On the campus of the University of Michigan is an example of the pool reactor. The water in the pool is demineralized to remove impurities that would become hazardously radioactive. A depth of 22 feet above the core provides shielding. Down at the core level, the beam holes and through tubes converge on the core to make use of the high neutron intensity, about 10 to the 13th neutrons per square centimeter per second when the reactor is operating at 1,000 kilowatts. The core of a pool reactor consists of a number of fuel elements mounted vertically on a grid plate, usually surrounded by reflector elements of beryllium or graphite encased in aluminum. Ion chambers and a fission chamber are added to detect neutron activity within the core. Each fuel element consists of a number of thin aluminum-clad fuel plates, spaced to permit free circulation of cooling water between them to carry off the heat. Plates are like a sandwich, having enriched uranium as the meat and aluminum as the bread. The aluminum cladding protects the uranium from corrosion and prevents the radioactive fission products from contaminating the water. A few fuel elements have several plates removed to provide a channel for inserting control rods. And movable control rods can be introduced among the fuel elements. A fuel loading consists of only 3 or 4 kilograms of enriched uranium in a small volume compared with the many tons of natural uranium in a graphite reactor. The water serves as moderator, coolant, and the major part of the shield. The core is mounted on a frame and suspended in the water from a motor-driven bridge across the pool. The bridge carries much of the operating equipment, including the safety and control rod drive assemblies. The design of research facilities varies for different pool-type reactors. At the University of Michigan, when access to the core through other beam holes or the thermal column itself is desired, the core is moved out across the pool and into another position. The far end of the pool is utilized for core storage and reloading. Here also, gamma-ray irradiation work may be done with highly radioactive used fuel elements. The instrumentation and operational controls are located in a control room overlooking the reactor. A wall diagram enables the operator to keep track of the fuel elements which are moved to suit various experiments and to compensate for burnup of uranium. Access to the thermal column is afforded from outside the pool at its base. Directly behind the sliding door is the graphite, with several stringers that can be readily removed for the insertion of samples to be irradiated by highly thermalized neutrons. Pool-type reactors provide a substantial number of beam holes, tubes, and other irradiation facilities for research purposes. This reactor has 12 beam holes converging on the core, and 2 large tubes that go entirely through the reactor, through the high neutron flux close to the core. There are also a number of pneumatic tubes to provide convenient short-time exposure of samples. During continuous operation, at power levels above a few hundred kilowatts, dissipation of the heat by natural convection becomes impractical. The water in the pool has to be pumped from the plenum to a heat exchanger, and the heat from the exchanger water dissipated from a cooling tower. A portion of the returning pool water is continually circulated through a demineralizer to remove dissolved minerals which could become radioactive. An open pool reactor can be designed to operate at a few megawatts. However, the design is complicated by increased pool depth, thicker shielding, and by thermal convections, which bring enough radioactive nitrogen-16 to the surface to create a radiation hazard. It becomes necessary to go to the tank-type reactor, a compressed pool in effect, to facilitate handling the cooling water. An example of this type is the Omega West reactor at Los Alamos Scientific Laboratory. The pool is only a few feet in diameter. Ordinary water, circulated by pumps, acts as both coolant and moderator. The top of the tank is sealed to allow slight pressurization to obtain sufficient water flow through the core of the reactor. The operating mechanism for the control rods is on the top. Also, the access hole through which the fuel elements are replaced. The elements contain enriched uranium in sandwich-type plates. Several ports are available for access to the core and the thermal column. In operation since early 1954, at the Argonne National Laboratory, near Chicago, is a tank-type research reactor using heavy water. It is called the CP5. The reactor portion of the building is sealed off from the rest of the structure by a double-door airlock and maintained at slightly less than atmospheric pressure. This safety measure is to guard against the escape of radioactive gases to the environment in the unlikely event of an accident. The reactor uses enriched uranium as fuel and heavy water for the reflector, coolant, and moderator. The heavy water permits a design that provides more space for irradiation of samples with less fuel. Because of the long neutron diffusion length in heavy water, high neutron fluxes of over 10 to the 13th at 2,000 kilowatts are available in a relatively large volume for experimental use. Graphite is used for a secondary reflector. The shielding consists of a thin boral liner to absorb thermal neutrons and a lead liner to reduce gamma-ray radiation. It is backed by a high-density concrete wall, nearly 5 feet thick. The tubular fuel elements contain enriched uranium, clad with aluminum. The cylindrical form provides access for fast neutron bombardment. Under normal operation, only 2 kilograms of uranium-235 are required for a fuel charge, which, because of fuel consumption, has to be replaced in about 6 months. 4 cadmium safety rods of the signal arm type move between the fuel elements to provide coarse control of the chain reaction. Fine control is provided by 1 cadmium regulating rod, operating vertically near the core. a flow of heavy water circulates through a heat exchanger and demineralizer and is returned. The radioactive nitrogen is confined to this system. A gas handling system provides for recombining deuterium and oxygen dissociated by radiation. At the top of the reactor, 45 vertical exposure holes are available for inserting and removing samples and fuel elements. The highly radioactive spent fuel elements are withdrawn into a lead coffin weighing approximately 8 tons and transferred to storage. The CP5 reactor has 2 large thermal columns, providing variable space for irradiation and other experimental work with slow neutrons. For beam experiments, 8 large beam holes are provided. The neutron flux is high at the face of the reactor because high-density concrete reduces the shield thickness. 2 special isotope channels extend under the core. 2 large through tubes pass close to the core, as do pneumatic tubes for quick exposure of samples. The Argonne CP5 reactor is designed primarily for neutron physics experiments, but it has been found useful for producing isotopes and for some engineering test experiments. A simple and relatively low-cost research reactor of low power but moderately high neutron flux is the Aqueous Homogeneous or solution type. The first reactor of this type was put into operation in 1943 at the Los Alamos Scientific Laboratory. Enlarged twice, the present version has been in use since 1950. In the city of Chicago, Illinois, another research reactor of the homogeneous type is operated by the Armour Research Foundation and financed jointly by 24 industrial firms. It is a simple and relatively low-cost research reactor of low power but fairly high neutron flux, more than 10 to the 12th neutrons at 50 kilowatts. The active core consists of enriched uranyl sulfate dissolved in distilled water. The water also serves as the moderator. The solution is held in a stainless steel sphere. Thus, the enriched fuel and the water moderator are homogeneous, as contrasted with the lattice arrangement of solid fuel in heterogeneous reactors. A reflector of graphite completely surrounds the core. Control rods enter thimbles built into the vessel. Water, circulating in a coil of stainless steel tubing, removes the heat generated by fission in the fuel solution. Leading from the core are other stainless steel pipes for handling the fuel and the gases resulting from the fissioning process and from radiolysis of the water. Above the core is an overflow assembly, providing a space into which the liquid fuel is ejected in case of a rapid power excursion resulting in a reactor shutdown. Neutron-absorbing control rods penetrate the sphere through the top. They are actuated by electric motor drives and a housing on top of the shield. To ensure against the accidental release of radioactivity to the surrounding area, this reactor utilizes a steel core vessel, an aluminum envelope, and an airtight room as a triple containment system. A gas-tight room containing the highly radioactive fission gas handling system provides an essentially neutron-free gamma irradiation facility. A large graphite thermal column includes several features which provide a variety of convenient exposure openings. There are 4 vertical beam tubes penetrating the graphite reflector, 2 pneumatic tubes for rapid exposure of samples, eight horizontal beam tubes that reach to the core, as well as an exposure tube through the center of the core. Instrumentation and controls are provided in a room above the reactor. As in all reactors, shutdown is easily accomplished by the use of the scram button. Because of its low fuel inventory of only 1,300 grams, its high flux-to-power ratio, its neutron-free gamma irradiation facility, and its compactness and relatively low cost, the solution-type reactor is finding wide acceptance and utility. At the Brookhaven National Laboratory near New York City is the United States' largest graphite research reactor. The reactor built in 1942 by Enrico Fermi was of this type. This multimillion-dollar reactor, at its full load power level of 30,000 kilowatts of heat, produces a high neutron flux over 10 to the 12th in a very large volume. Behind the 5-foot wall of what we see simply as a concrete box is the natural uranium fuel in horizontal channels through a large mass of graphite moderator. The core is a cube measuring about 25 feet on the side. A neutron reflector of graphite surrounds the core. Control rods operate in the fuel zone. The heat produced in the core is removed by air. And finally, the reactor is enclosed in a thick concrete shield. There are 700 tons of graphite in the 25-foot cube. Through this run nearly 1,400 fuel channels. In the original fuel element, 33 natural uranium slugs fit into an aluminum cartridge, which was sealed to prevent corrosion and the escape of radioactive fission products. The uranium slugs were encased in an aluminum cartridge with fins to aid transfer of heat of fission to the cooling air. Using these elements, the natural uranium loading was approximately 55 tons. However, the natural uranium has been replaced with a new type fuel element, with enriched uranium in curved sandwich-type plates of aluminum, requiring only about 60 kilograms of fuel for a loading. The result? A 4 to 5 times increase in flux density without going to higher power. At full power, the temperature of this air leaving the reactor is 350 degrees Fahrenheit. 5 1,500 horsepower exhaust fans pull 750 tons of filtered air through the fuel channels every hour at velocities approaching the speed of sound, and discharge it harmlessly to the atmosphere. The reactor is operated from a control room which is manned around the clock. Safety is a primary consideration. Many independent checkpoints automatically shut down the reactor if the power level goes too high, if fuel temperature becomes excessive, or other abnormal operating conditions occur. A chief advantage of the natural uranium graphite reactor is the numerous openings and very large spaces it provides for experimental purposes, with thermal neutron fluxes as high as 10 to the 13th, quite adequate for most purposes. Coming out from the core are 30 experimental holes, which provide neutrons for experiments either outside or inside the reactor. 11 pneumatic rabbit tubes penetrate the reactor to the center of the core to provide very short-lived radioisotopes for immediate laboratory use before much of the activity is lost. On top of the reactor also are many large openings. Although the capital investment is high, the large irradiation space and natural uranium fuel offer many unique features. Most research reactors clearly belong to one of these 4 basic types. However, numerous adaptations are being tried, and new types may be developed. At the Argonne National Laboratory is an adaptation of the tank type. It is called the Argonaut and is useful for some research, but designed primarily for nuclear technology training. At full power of a few kilowatts, it produces up to 10 to the 11th thermal neutrons per square centimeter per second. Built into this low-cost, low-power reactor are many features of convenience, safety, and flexibility. At one end is a thermal column, and at the other a movable tank for conducting shielding experiments. The reactor design is so simple that laboratory people are urged to build it themselves. The annular shape of the reactor vessel makes possible arrangements of aluminum-clad fuel plates in a ring around an internal graphite reflector. Approximately 4 kilograms of U-235 in 20% material are used, and plates can be put in different positions to meet the needs of the experiment. Within the graphite center are 5 access holes. The outside of the tank is also surrounded by graphite, in which the control elements are located. Ordinary water is pumped through the tank as both coolant and moderator. The instrumentation and controls consist of easily procured standard devices. The uses of the Argonaut in training include startup, criticality experiments and reactor operation, demonstrations in engineering and nuclear physics, and a variety of research experiments. Other very low power reactors have been developed by industry. For example, solid homogeneous reactors are being built to operate at a few watts to serve training and limited research needs. They offer the unique feature of complete portability as well as safety in operation. Its fuel consists of less than 700 grams of uranium-235 at 20% enrichment. Uranium oxide is mixed with solid polyethylene moderator and molded into discs which are housed in a graphite reflector and shielded by lead and water. The small size, portability, and low cost make the solid homogeneous reactor a practical classroom trainer. A low-power solution type homogeneous reactor with a flux of 10 to the 8th has also been developed. The reactor is fueled with about 1,500 grams of uranium-235 in 20% material. It is dissolved in 20 liters of uranyl sulfate in a small stainless steel sphere. This core, surrounded by a lead reflector shield, is housed in an 8-foot diameter tank of water. This reactor is suitable for low-flux research and training. It can be shipped as a unit, and its small size makes it practical for use in schools. Research reactors are contributing to a continual program of experimentation and research, probing and serving the fields of chemistry, physics, metallurgy, biology, and medicine. The most familiar use is the production of radioisotopes. Several hundred radioactive isotopes, one or more for nearly every element in the periodic table, are being employed in research, medicine, and industry. For example, they are used as tags in tracer study of every description. The measurement of fertilizer uptake in plants. The diagnosis of thyroid carcinoma and other diseases by obtaining with the centiscanner a plot of the localization of radioisotope deposit in the glands. In the field of chemistry, radioisotopes trace the behavior of elements and compounds in chemical reaction. Special machines using large gamma sources of cobalt-60 produced in high-flux reactors are employed in the treatment of cancer and leukemia, and in industry for making radioautographs of dense structure. Radioisotopes are used in density gauges for various industrial purposes, such as continuously measuring and controlling the thickness of a plastic sheet. In addition to the production of radioisotopes, another major use of the research reactor is in the study of basic physics. Several experiments may be conducted simultaneously, such as the continuous cloud chamber experiment, the neutron diffraction spectrometer experiment to study crystalline structure of elements and compounds, the time of flight spectrometer. It employs a mechanical rotor or neutron chopper, a long flight tube, and a 1,000-channel analyzer. This experiment measures nuclear cross-sections of isotopes. For capture gamma ray studies, the bent crystal spectrometer is used to cover the gamma range from a few thousand to several million electron volts. Irradiation of materials by fast neutrons produces changes in such mechanical properties as tensile strength, creep and shear, and significant changes in electrical and thermal conductivity. For effective engineering studies of changes in metals, samples must be irradiated to a total exposure of about 10 to the 18th neutrons per square centimeter. Only with very high flux test reactors can such irradiations be made in a reasonable time. In biology, mice and rats are utilized for radiation experiments. A study of the effect of radiation on bone marrow in immunity and genealogy. Reactors of low fluxes are used for activation analyses. A quantitative analysis can be made faster, and in some cases more accurately than by conventional chemical means. Irradiated fuel elements provide an intense source of pure gamma rays for food irradiation studies. Pasteurization of foods and drugs allow for longer storage life. These are but a few of the rapidly multiplying applications of research reactors. A practical program that utilizes a research reactor involves a considerable financial investment. Detailed planning and care must be exercised in the selection of the type of research reactor for a particular program. Only a realistic, objective review and appraisal of the broad aims of an organization, its research needs or training requirements, can determine this selection. Where research requires a reactor capable of producing neutron fluxes in the range of 10 to the 12th to 10 to the 13th, the pool type will do the job. Another is the homogeneous reactor, which also produces fluxes in this range, but in a smaller volume and at a lower operating cost. The tank type using heavy water provides a larger volume of irradiation space at these fluxes. The greater volume makes possible a large research program, but the cost of heavy water must be justified by the research needs. The graphite moderated type, with the same flux in a very large volume, can support an extensive research program. Where the neutron fluxes required are substantially above the 10 to the 12th to 10 to the 13th range, a reactor for materials or engineering testing is essential. In limited research programs and for teaching purposes, a simple low-flux reactor may satisfy the need. The procurement of the reactor itself is not the only financial obligation imposed on a research program. There is also the need for associated equipment and facilities, manpower, and supplies. An entire scientific community, including chemical, physical, biological, metallurgical, and other laboratories, are all essential facilities. Intensely radioactive specimens must be handled in hot cells, equipped with intricate remote control devices. Heavy shields of dense concrete with special shielding windows protect the operator while specimens are processed and examined. A counting room is necessary, shielded to protect counting devices from outside radiation. An electronics shop for the maintenance of sensitive controlling, measuring, and recording devices. Personnel must be trained for the operation and maintenance of the reactor. All of these are important considerations for the organization that undertakes a research program with a reactor. Wisely, the functional requirements of the reactor will be kept close to the needs of the planned program. The nuclear reactor is a powerful research tool, offering to every branch of science new horizons in the service and needs of mankind.